All right, folks, in a typical collision problem, instead of going from point A to point B like we did when we conserved energy, we're going to look immediately before the collision and immediately after. So later on in the unit, I'm going to say this is like A and A prime. The time that the collision lasts is so short that we often just say, pretend like it happened instantaneously, even though it doesn't. Okay, my point is, instead of looking at point A to point B and saying T me A equals T me B, we're going to say the sum of the momentum of the system, which is why we talked about systems early in the year, equals the sum of the momentum of the system. Actually, we tend to say initial and final because it's before and after. Okay, and then what is momentum? It is mass times velocity. So we have two objects that might have mass and velocity. And then we love inelastic collisions because they stick and become one single mass. I'm going to call that m tote times v final. Okay, so all of the momentum before has to equal all of the momentum after. And this is what I call a work backwards problem because you know more information about the after. So just like when we did conservation of energy, there was, like for the bungee jumper on the bridge, there was one point, and it wasn't always point A, but there was one point at which you knew all the energy. You knew the height, the speed, and the spring start energy. Same thing. You're going to know either the before or the after. But just trust that you're going to figure it out and start with, instead of T me A equals T me B, you're going to say sum of the momentum equals sum of the momentum. Okay, so what was a little annoying was they gave you the mass of the bullet in grams. So it is 10 times 10 to the minus 3 kilograms times the initial speed of the bullet. The block was at rest, so that is 0, so we can cross that term out. And they stick together, so it's 5.01 kilograms total, and times V final, which is 0.06. And if you solve that for V initial of the bullet, you get 300.6 meters per second. Really fast, right? Because that's what bullets do. Okay, awesome. That was question 15. All right, now we have a railroad car, and I will pause to draw the pictures. Okay, so here you have your before picture where you have a railroad car going 4 meters per second, collides into 3 identical railroad cars going at 2, and since they're going more slowly, this is going to run into those. And then they latch, they attach, and they will end up as one solid single object going off at some final speed that we're going to calculate. Okay, so we have before and after. There's no outside forces, so momentum is conserved. And we have, the sum of MVs equals the sum of MVs. And you've got 2.5 times 10 to the 4th, my 4s draw weird on my tablet, times 4 meters per second plus 3 of the same things, going 2 meters per second. So that's our before system, right? Just like we added up different kinds of energy, we're adding up all of the momentum. And then after, they stick together, so you have a total of 4 times 2.5 times 10 to the 4th kilograms, going some speed we don't know. Okay, now the mass is in every term, so this actually will cancel, which gives us 4 plus 6, because we got a 2 going on here, and 3 there. Equals 4V final, right? So V final is 10/4, which is 2.5 meters per second. Okay, so let's check to see if that makes sense. You can kind of think of this as kind of being like a weighted average, maybe, where you got a speed of 2 weighted by 3 identical things and a speed of 4, but there's only one of those. So on average, their speed is 2.5, right? So it's got to be a little bit more than 2, but these are going to dominate because there's 3 of them and only one of those. Okay, so awesome. That is the speed. And then you should know, I don't care if you're taking the AP or not, you should absolutely know whenever things collide and stick, you will always lose energy. Always. Complicated story. I'll send you the article that I wrote on it. It is, but you should know you are always going to lose energy if things run into each other and stick. So we will calculate that in a second. All right. So now we want to see how much energy is transformed into internal energy. So this is a little confusing because there's no external forces. Like, that's why these are on wheels. There's no friction taking energy away. Otherwise, we couldn't have conserved momentum. But there is energy loss. So what's a little confusing is when things collide, they're going to squish and unsquish. And in the unsquishing, when those molecules rebound, they don't give back all the energy. Kind of like when you bounce a basketball and it squishes and it unsquishes and it doesn't come up to the exact same height as before. So that energy is still in the system because these railroad cars are warmer than they were before. So it's still kind of in the system, but we're still going to say it's lost because it's internal energy. It's heat. So we're going to still say TMEA plus work. And remember that work is only supposed to be from external forces equals TMEB. So it is a little bit contradictory, I would agree. But I think it makes sense that it's lost to heat. Okay, and we're just saying that even though those molecules are part of the railroad car, they are not, their internal kinetic energy is not part of what we're defining as a system. Okay. The math isn't hard. Conceptually, it's a little bit goofy, I will admit. Okay, so what's nice about these is that often you're just calculating kinetic energy. There are problems where then these will go up a hill or compress a spring, but clearly you got motion before and motion after. So it's pretty straightforward to say, I'm going to add up all of the 1/2 mv squared terms that I have in the beginning, and I'm going to find that those are going to be different than the 1/2 mv squared term I have at the end. Okay, so it's pretty plug and chug. Here the mass doesn't cancel because we need to know how many joules. Be careful with calculating all of your mass because you've got 3 of these puppies. Okay, so all of that blue, that's all the before. You got 1 railroad car plus 3 railroad cars plus what happened to it equals 1/2 4 times 2.5 times 10 to the 4th times V final, which we found out was 2.5 squared. Okay. Running through the math, you get that you initially had 350,000 joules of energy. And at the end, this turns into 312, 500 joules of energy. And so when you take the difference between those two, you find the work done. This minus that is negative 37,500 joules. Okay, and that's a pretty classic problem. Things will collide and stick, and they are still moving, so you're just going to take the difference in kinetic energy. Moral of the story is you need to make sure that you include everything that's moving before and after. All right, that was 16. Hope that one made sense. All right, this is a classic problem too, where something is moving along and then something else is dropped onto it, like maybe there's a skateboard sliding along and then a kid jumps on it, and it's a collision. And so here's the information. You got your before picture and your after picture. What's a little confusing is Batman definitely has some kind of vertical velocity. That momentum is taken away from the outside force of the normal, like that clearly is no longer there. So that momentum isn't conserved, but horizontally, the momentum is going to be conserved. So again, you get a point on the AP for saying, I understand this is a momentum problem, the sum of the momentum is conserved. You could start with sum of MV equals sum of MV if you want. And so be careful, we're doing X only horizontal. Velocity is a vector, so you got to separate the horizontal and vertical. So therefore more momentum is a vector. So the Batman has no horizontal velocity, so therefore he has no horizontal momentum. So we just have the boat. Yeah, it's a boat that is traveling along at 11 meters per second. And the mass increases. I did that addition for you to 610 kilograms and some final speed. And you get that the final speed, it has decreased from 11 to 9.33 meters per second. Okay, so pretty straightforward problem. Just trying to mix things up a little bit, that the collision kind of happened from the sky, you know, up and down instead of left and right like the first one did, or the second one did. All right, that was 31. 34 is a classic as well. It was an AP problem. Those of you taking the AP, you can see that this, after it leaves the incline, it'll become a projectile. That's why the first module was projectile module. So hopefully more motivation, reason to go back and look at that. So we have a chunk of coal that gets spit off of a chute, and it collides with this car on the track. So it's just like one more step complicated than the one we just did. Again, momentum is really a two-dimensional problem. Once on the AP, they had a two-dimensional collision. You just conserve momentum horizontally and vertically. Just keep it separate like we did for forces. Okay, so the first thing you need to do is, if anybody wants me to post some of those, if you're taking the AP, I'm happy to do that, but it's pretty easy to figure out how to do that. So we need to figure out how much of this coal is traveling horizontally and how much is vertical. So the horizontal speed is 0.8 times the cosine of 25, which is a measly 0.725 meters per second. Just like Batman, the one we just did, there is some V0y, but that momentum, that downward momentum, is going to not be conserved because of the outside force of the floor. Okay, so we only care about the horizontal motion so that we can now conserve momentum in the horizontal direction. Okay, so we have a piece of coal with a horizontal speed. We have a, whatever they call this, a car. Technically, these should have subscripts. Times its own, and actually this is initial, lots and lots of subscripts. I'm just trying to save time. So you can look at the paper answers if you want more thorough subscripts and paying attention. They stick together. Again, that's the whole point of these. We love these kind of problems because this is easy. We're only going to have one final term. This is going to be the total mass times the final speed. Okay, so this is the piece of coal. That is a massive piece of coal going slowly. That's in kilograms, that's in meters per second, plus the cart going also not very fast, equals m tote 590 kilograms times how fast they are going at the end of the collision. This is 108.75. This is a beautiful 220 equals 590 VF. That means the final speed is about a little bit over a half a meter per second. Let's see if that makes sense. This was going 0.5. It was heavier. And this was going 0.725. So that's going to shift the total speed up. And it ends up going 0.557 total together. I'm going to briefly talk, if you want to listen to that, like what, if you think about why that makes sense, here's the cart that is moving. Since the coal is moving faster than that, you can see it's going to, it has inertia, it wants to keep going. So it's going to literally run into this front wall of the 440 kilogram, whatever this is, coal mine car. It's going to slam into that, which is going to speed the cart up. And by Newton's third law, the wall of the car is going to push the piece of coal to the left, which is going to slow it down, right? So this 0.5 is going to increase because it's being pushed by the coal. The 0.725 is going to decrease because it's being pushed to the left by the wall, and they're going to meet in the middle at 0.557. Again, it's not the numeric middle because it's, again, it's a weighted average based on how much mass is going which fast, how fast. But conceptually, it should make sense. This is being pushed opposite its motion, so this is going to slow down. This is being pushed with the motion, so it's going to speed up until they have the same speed. Okay, that's the concept. And hopefully this all makes sense. Keep on practicing.